Oumuamua came through our solar system. It passed by the sun, and it accelerated. It accelerated like something with a push behind it. That was the first thing we ever saw from another star. Astronomer Avi Loeb looked at it. He put forward an idea. The simplest explanation, he said, might be that it was built, that it was made by an intelligence. This one object, this rock, it's made scientists change things. They've had to rewrite the rules because of how it moved. It moved in a way that gravity alone doesn't explain. So we have to look at it. Was it just a natural thing, a strange rock? Or was it a piece of technology, something made, and then what it means for us? For humanity out in the cosmos, if this was the greatest thing we've found, and it might be a message we don't know how to read yet. That faint point of light, it didn't belong. October 19, 2017. A telescope in Hawaii on a volcano doing its nightly scan, looking for things that move against the stars, and that night it found one. The data was strange. Its path wasn't a loop, not an orbit around our sun like everything else. It was a wide curve, an open curve, with so much energy it could only mean one thing. This thing wasn't from here. It was passing through from the space between the stars. It sent a jolt through the astronomers who watch for this. For the first time, we saw an interstellar object. A piece of another star system. Traveled light years to pass through ours. They gave it a Hawaiian name. Oumuamua, it means scout. Messenger from the distant past. The first thing we ever saw from beyond our sun, and we named it a herald, a scout. Sent from the deep past of another star arriving at our door. The first observations showed a strange traveler. Moving incredibly fast, over 196,000 miles per hour as it went around the sun. Telescopes tried to see more, but it was just a pixel of light. They looked for the halo of gas and dust a comet makes. Oumuamua had none, it was dark, and it was tumbling, rotating chaotically like a bottle in waves. That was the moment astronomy changed. It wasn't theory anymore that stuff from other stars could visit. This was the proof, tumbling through the void. It laid a foundation for a new kind of object and for a deep mystery. Because if this was our first interstellar messenger, then the question became right away, what message was it carrying? The first real clue was an absence, something missing. When a comet gets close to the sun, the ice on it doesn't melt. It turns straight to gas, that's sublimation. The gas and dust stream off, and that forms the coma, the glowing halo, and often a tail. That outgassing acts like a tiny rocket. It pushes the comet, changes its orbit. It's a known force. So when Oumuamua was seen accelerating after its closest approach, the logical thought was outgassing. It must be a comet, a dark one, a strange one. So they looked. Hubble, the big observatories, they searched for water vapor, carbon dioxide, any dust reflecting light. They looked for the faint glow of a coma. And they found nothing. The data was clear. Oumuamua was pristine, dark, inert, no tail, no cloud of gas or dust. That was puzzling. If the acceleration wasn't from outgassing, what was pushing it? The simple explanation was gone. It was behaving like a comet in one way by speeding up, but looking nothing like a comet in any other way. That contradiction changed things. It moved the mystery from a curiosity to something deeper. It forced scientists to set the textbook aside, to start considering possibilities right at the edge of our understanding. If not gas, then what? The numbers were clear. After the closest pass, as it was moving away, the path changed. Not a lot, but enough. The orbital calculations, the ones that predict spacecraft trajectories with precision, showed a small, steady nudge. Something besides gravity was acting on Oumuamua. It was accelerating away just slightly, like it got a gentle push. That's a non-gravitational acceleration. It means something other than a massive object's pull is affecting the course. Normally, that's a comet outgassing. But Oumuamua had no visible coma, no gas we could detect. So the source of the push was invisible. It's like a sailboat on still water. If it starts moving, you look for wind in the sails. But this was a boat moving with its sails down and no wind to feel. The push was in the data, a whisper in the math, but its origin was a complete blank. That was the core anomaly. The shape, the darkness, the tumble, those were odd. But this acceleration broke the expected script. It was doing something active. That tiny deviation, that faint signal against all that celestial motion, became the central evidence. It forced one question. If the simplest explanation, outgassing, was ruled out by what we saw, then what other forces could be at work, natural or otherwise? Science had to get creative with this invisible push. The first serious natural explanation was something exotic. Maybe Oumuamua wasn't a rock. Maybe it was a cosmic iceberg made of something stranger. Molecular hydrogen ice. That idea came from researchers like Daryl Seligman and Gregory Laughlin. They did the math. If Oumuamua was mostly solid hydrogen, it could solve the mystery. Hydrogen ice sublimates. It turns straight from solid to gas when the sun warms it. And that gas would be completely invisible. No dust, no glowing cloud. A perfectly stealthy engine. The exact kind of gentle, steady thrust to match the data. A hydrogen iceberg could be the answer. A natural object, but one we'd never seen before. The idea is elegant in its simplicity. It uses a known process, sublimation, but with a material we almost never find in pure, solid form. It explains the lack of a visible coma. For a moment, the math seemed to work. It kept Oumuamua in the realm of natural phenomena. Just a very, very rare one. A cosmic snowball made of the universe's most basic element, drifting between stars. But this hypothesis ran straight into the harsh realities of interstellar space. The first big problem is formation. Where do you get a chunk of solid hydrogen the size of a city block? Molecular hydrogen ice only forms in the coldest, most isolated places, like the dense cores of giant molecular clouds. Even there, the conditions to make a massive, cohesive iceberg are extraordinarily rare. It's like a perfect snowflake forming and surviving in a desert. The environment is against it. Then there's the journey. Interstellar space isn't empty. It's filled with starlight, cosmic rays, the sparse interstellar medium. A hydrogen iceberg would be fragile. Over millions of years of travel, that relentless starlight would have slowly eroded it. By the time it reached us, many critics argued, it would have evaporated long before. The idea of it surviving an epic voyage to arrive intact stretches probability. So the hydrogen iceberg theory is brilliant creative problem solving. But it asks you to believe in an object of profound rarity and even more profound fragility. It solves one puzzle by presenting another, maybe greater one. The search for a simpler answer wasn't over. There's another idea that takes fragility to the extreme. What if Oumuamua wasn't solid? What if it was just fluff? A cosmic dust bunny? A fractal aggregate, dust and ice clinging together, mostly empty space? Picture a dandelion seed head, or that airy clump of dust under a bed. That's what this theory says it was. An object so low in density it was almost nothing. And that changes how the push works. Sunlight carries momentum. Photons exert a tiny pressure when they hit something. For a planet or an asteroid, that pressure is nothing. But for something with almost no mass, a puff of fluff, that gentle pressure from light itself could be enough. It could act like a natural solar sail. The acceleration we saw wouldn't come from gas jetting out. It would be light, pushing on this vast, porous surface. It's an elegant idea. It explains the thrust without needing invisible gas. The object, being so dark and fractal, could have absorbed that sunlight perfectly, turned it into that subtle, steady nudge away from the sun. This paints a different picture of interstellar material. Not hardy rocks, but delicate, ephemeral structures. Drifting between the stars, it expands what we imagine could be out there. But then, fragility. Could a dandelion seed survive a hurricane? As Oumuamua whipped around the sun, it faced intense heat and tidal forces. The sun's gravity pulls harder on the near side than the far side. For a solid rock, that's fine. For a dust bunny held together by the weakest forces, that stretch could be catastrophic. It should have been torn apart. Or the sunlight pressure that supposedly pushed it. That same pressure should have blown it apart long before it ever reached us. And the journey through interstellar space isn't gentle. It's a bombardment. Cosmic rays, micrometeoroids. A structure that delicate seems unlikely to survive a voyage lasting millions of years. So the dust bunny model accounts for the acceleration, but it creates this profound puzzle of durability. It asks you to believe in a ghost of an object. A whisper of structure, enduring an odyssey that should have erased it completely. Every natural explanation required a leap of faith. A hydrogen iceberg that shouldn't have made the trip. A dust cloud that shouldn't have survived the sun. The data was stubborn. The simple answers kept falling short. So maybe the simplest answer wasn't natural at all. Maybe it was a piece of technology. That's the idea from the Harvard astronomer Avi Loeb. He looked at the same facts. The acceleration, no coma, the strange shape, and he asked a different question. What if this was built? Not a rock, not an iceberg, but a light sail, a piece of machinery from another civilization. The light sail concept, it's not science fiction. We're building them now. The idea is simple. You don't carry heavy fuel. You use a giant, thin, reflective sheet. Photons, the particles of light from a star, they carry a tiny bit of momentum. They hit that reflective sheet and they push. It's a gentle push, but it's constant. And over time, in the frictionless space, that push adds up. It adds up to incredible speed. A light sail can travel between stars without fuel. It just rides the starlight. Now take Oumuamua. Its mysterious acceleration. That push we saw was exactly what you'd expect from a light sail. A gentle, steady nudge away from the sun, powered by sunlight. It perfectly fits the data. No invisible gas, no improbable fluff. It uses a propulsion method we already understand. The other oddities fit, too. Its extreme shape, which we inferred from how its brightness changed as it tumbled. That could be the profile of a thin, pancake-like sail. Its high reflectivity, which astronomers figured out later. That's exactly what you'd want for a sail designed to catch the light. In this view, Oumuamua wasn't tumbling chaotically. It might have been drifting. Its orientation no longer controlled. A piece of a larger structure that broke apart. A discarded probe, its mission over. Now just cosmic debris on an endless journey. This idea does more than solve a physics puzzle. It shifts the whole conversation. It moves us from astrophysics to astrobiology, from studying rocks to searching for intelligence. If this is right, then Oumuamua wasn't just a visitor. It was a message written in the language of engineering and light, and it passed right through our solar system without us knowing how to read it. The implications are staggering. It suggests we are not alone, that the artifacts of other minds are already here, drifting silently in the dark. They saw a faint signal in the data. A dot of light. They watched its pulse, the way its brightness changed. Not randomly, it had a steady, repeating rhythm. That's the light curve. It's like listening to a distant lighthouse. The pattern of flashes tells you about the shape of the thing that's spinning. If an object is a sphere, a ball, its brightness stays constant. But if it's long and thin, like a cigar, or flat, like a pancake, the amount of surface area facing you changes. When the long side faces Earth, it reflects more sunlight. It looks bright. When it turns to show just the thin edge, it nearly vanishes. The light curve is a shadow play. It reveals form through brightness. Oumuamua's light curve was extreme. Its brightness varied by a factor of 10. It didn't just get a little brighter or dimmer. It would shine, then almost disappear, then shine again. That tenfold swing is enormous. In our entire solar system, among all the asteroids and comets, nothing natural varies that much. The closest things are a few odd, elongated asteroids, but even they only vary by a factor of 3 or 4. Oumuamua was in a class by itself. To produce that kind of variation, the math points to one conclusion. An object that is at least 10 times longer than it is wide. Picture a cigar. 10 inches long but only 1 inch thick. Or, and this is critical, a flat disk. A sheet. A pancake tumbling end over end would create the exact same pattern. A brief, brilliant flash when the broad face glances at us, then a long period of near darkness as it shows only its edge. So which was it? A cosmic cigar or a celestial pancake? Later analysis tilted the scales. They studied how it reflected light. Oumuamua was surprisingly shiny. More reflective than a typical comet. That high reflectivity, that albedo, is harder to explain for a rough, rocky cigar tumbling through space for eons. It would be expected to be dark, scarred by impacts, but a thin, manufactured sail, a smooth, reflective surface designed to catch starlight, that fits perfectly. This shape, inferred from the silent language of flickering light, became a tangible clue. It wasn't just a weird rock. It was a weird rock with geometry. A form so extreme it pushed against everything we know about how natural objects form. Rocks in space tend to become roughly spherical over time, from collisions and their own gravity. Something this elongated or this flat is an outlier. It suggests a different history. Perhaps it was shorn off a larger object in a violent collision, stretched and melted. Or perhaps it was never formed by collisions at all. Perhaps it was constructed. The light curve gave the mystery a silhouette. It turned an abstract dot into an object with proportions. And those proportions whispered a question. Are we looking at a singular natural accident, or the deliberate lines of a craft built to sail on sunlight? That flicker of light gave us a shape, and then it gave us a color, and from that you could infer a texture from how it reflected the sun. That reflectivity has a name, albedo. Fresh snow, blinding white, that's high albedo. A piece of charcoal, that's low albedo. Most things from the outer solar system, asteroids and comets, they're like cosmic charcoal. Dark, primitive, unchanged, they have low albedo. So when they looked at Oumuamua's light, the result was a surprise. It wasn't dark. It was shiny, moderately shiny, some estimates said highly reflective. Its surface acted more like polished metal or a clean sheet of ice, not an ancient, sooty rock. That measurement became a key piece. A highly reflective surface is what you design for a light sail. Efficiency is everything. You want to catch every photon to maximize that gentle push. A dark surface would absorb the light, turn it to heat, not momentum. So a shiny Oumuamua fit the artificial idea. But nature has shiny things too. A comet that's never been near a star could have a pristine, icy crust. A body fractured in a collision could expose a bright, metallic interior. So the reflectivity alone wasn't proof. It was an intriguing clue. It made the artificial idea more plausible without ruling out the natural. The real challenge was getting the measurement. Oumuamua was a faint, speeding pixel. It was already racing away when we saw it. Astronomers had fleeting glimpses. They compared its brightness in different wavelengths. Different telescopes, different teams, all working with the slimmest data. Sometimes they arrived at slightly different numbers. Was it as reflective as fresh ice, or more like a dull rock? The uncertainty was part of the story. Even something as basic as how shiny it was that was shrouded in debate. This wasn't a flaw in the science. It was a testament to the object's elusiveness. It was a visitor that refused to be easily categorized. Its basic properties were just out of reach. Every interpretation had to live with ambiguity. And that ambiguity, in the end, became the fuel for the mystery. It created the space where both the natural and the extraordinary could be argued. The reflectivity data didn't solve the case. It just asked a question: which narrative does this shiny surface best reflect? Space isn't ever completely quiet. There's a hum, the leftover whisper from the Big Bang. There's crackling, radio waves from stars and galaxies far away. So when something came from beyond our star, one question got urgent. Was it humming something itself? Was there a signal in all that cosmic noise, some whisper of technology? If there was any chance Oumuamua was more than just a rock, we had to listen. We had to point our best ears toward it and hope. This wasn't just curiosity, it was a test. Breakthrough Listen led it, a project built to scan the sky for signs of intelligence. They had the tools. The Green Bank Telescope in West Virginia, a colossal dish, one of the largest fully steerable radio telescopes on Earth. It can hear the faintest whispers across the galaxy. In December 2017, as Oumuamua was already speeding away, they pointed Green Bank at it. They tuned its receivers across 4 wide radio bands, covering billions of individual channels. They were listening for a narrowband signal, a focused beam of radio waves, the kind a transmitter makes. Not the broad, messy static from a star or a quasar, but a clean, artificial tone. A beacon. For 10 hours over 3 separate observing periods, the giant dish collected every photon of radio energy it could from that distant point. The data was immense. Then came the analysis, sifting through all that noise, looking for a pattern that didn't belong, a repeating pulse, a structured sequence. Anything that said, "I am here, I was made." The result was profound silence, no pulses, no carriers, no signs of technology, just the natural hiss of the universe. That null result is a crucial piece of data. It didn't prove Oumuamua was natural, but it strongly suggested it wasn't what we might have hoped for: an active, broadcasting probe. It wasn't chatting with home or sending out a greeting. It was inert, a silent traveler, and that, in a way, opens a door to an even stranger possibility. What if it was a derelict, a piece of discarded technology, its power long dead, tumbling dark and cold through the void? Or a passive artifact, like a monument or a marker, never meant to broadcast at all? This changes the entire framework of the search. We've often imagined first contact as a signal, a message we decode. But what if the first evidence is garbage? A spent fuel tank, a broken sail, a piece of debris from a civilization that may have risen and fallen a million years ago. We wouldn't find a message. We'd find archaeology, a silent, physical clue to a story we can only guess at. The search for radio signals taught us something vital. It taught us to listen for silence, too. And to wonder what kind of stories a silent object might carry. The silence wasn't an ending. It was a different kind of signal. It moved the conversation out of the telescopes and into the lecture halls. Into the journals. This stopped being about data points. It became a philosophical argument, a fight over how science should act when it meets the truly unknown. On one side, there's a very old rule. Extraordinary claims need extraordinary evidence. For most astronomers, Oumuamua was strange but not proof. They look at history. Every time we've seen something bizarre out there, the answer wasn't aliens. It was new physics. Pulsars, those perfect cosmic ticks, were called LGM. Little green men, but they were neutron stars. The universe can make things we haven't even imagined yet. Michelle Bannister has this view. She says we've barely started cataloging the objects in our own solar system. The ones from other stars, we know even less. Jumping to an artificial explanation isn't bold to her, it's a shortcut. It might shut down curiosity. Why invent an untestable idea when the anomaly could push us to find a new kind of natural object? Hydrogen icebergs, fractal dust clouds, that's the frontier being redrawn right now. This isn't about being closed off. It's about discipline. Exhaust every natural possibility, no matter how novel, before making that ultimate leap. It's the engine of conservative science, the one that built our reliable picture of the cosmos. Then there's the other side, Avi Loeb. He flips the caution argument. What if our conservatism is the blindness? What if insisting on only natural explanations, no matter how contrived, is a bias that blocks a paradigm shift? He points to Galileo. The establishment refused to look through his telescope because imperfections in the heavens violated their philosophy. Loeb sees a modern version. The doctrine now is that we are alone, or that aliens are too improbable to consider. He argues when you have an object that matches several predicted signs of an artificial light sail, its acceleration, its shape, its reflectivity, And every natural explanation requires one unprecedented, fragile object after another. Then the simplest explanation changes. The simplest explanation might be that it's exactly what it looks like. For Loeb, the real risk isn't in speculating about intelligence. The real risk is ignoring a monumental discovery because we were too afraid to say the words. This is more than an academic debate. It's about the soul of discovery. Is science just a slow grind until the answer is unavoidable? Or is it also a leap? A willingness to follow the evidence into the most profound possibilities, even if it shakes everything. Oumuamua became the battleground for that. And the outcome wouldn't just decide what that object was. It would decide how we greet every strange visitor that comes after. The debate around Oumuamua, it's not the first time we've heard something like this. There was another moment almost 50 years back. A night in Ohio, a radio telescope was listening, just sweeping the sky. This was August 15, 1977. The Big Ear telescope. And a volunteer, Jerry Amon, he was going through the data printout. He saw a column of numbers and letters, and one sequence just stood out. It was so strong, so clean, he circled it, and in the margin he wrote one word, wow, the wow signal. It lasted 72 seconds. It came from the direction of Sagittarius. And it was exactly what they were listening for. A powerful, narrowband radio burst, focused on one frequency, the kind of thing a transmitter would make. Not the broad static from a star or a quasar. It had the signature of technology. It was the signal, and then it was gone. They looked for it again for decades. They pointed every instrument they had toward that patch of sky. They never heard it again. It was a single shout, a brilliant shout in the dark, and then a silence that's lasted generations. That event became a monument in the search. It taught a hard lesson. In astronomy, anomalies happen, a blip on a chart. A point of light does something strange. And sometimes, no matter how hard you look, you can't find it again. You can't confirm it. The wow signal sits there, a profound mystery, unresolved to this day. Was it a message, a beacon that flashed just once? Or was it a natural phenomenon we still don't understand? Maybe a passing comet, emitting a freak burst of radio waves. Maybe something else entirely. The data is too sparse. The event was too singular. The lesson from 1977 is humility. The universe is vast and strange. Our tools are limited. We catch glimpses, we record anomalies, and we have to live with the fact that some mysteries may never get a final answer. They become part of the landscape, reminding us how much we don't know. Oumuamua is a different kind of wow signal. It's not a blip on a radio chart. It's a physical object. We tracked its path. We measured its light. We have data on its acceleration, its shape. It's a tangible anomaly, something you could point to, an actual visitor that passed through our neighborhood. That changes the game. It moves the mystery from a fleeting signal to a solid thing. We can't dismiss it as an instrument glitch or a one-time burst. It was there, it happened. So the old lesson of humility still applies, but now it's under a new pressure. When the anomaly has mass and trajectory, when it leaves a gravitational signature, the need for an explanation becomes more urgent. It pushes us to decide, do we accept a series of highly unusual natural explanations, each one requiring a new, fragile type of object we've never seen? Or do we allow ourselves to consider that the simplest explanation might be the most extraordinary one? Oumuamua forces that choice in a way the wow signal never could. It gives the cosmic whisper a shape, and in doing that, it asks a louder question, a more persistent one. Oumuamua was almost missed. It was a whisper against the stars. But the discovery wasn't an accident. It came from a new kind of watchman, a telescope built for vigilance that spans stars. It sits on a volcano in Hawaii. Its job is relentless. Night after night, it scans the sky with a huge camera, one of the largest ever built. It's not looking for one thing, it's looking for anything that moves. It takes images of the same area over and over. A computer compares them, it subtracts the static stars, it searches for the points of light that have shifted. Asteroids, comets, anything moving in our solar system gets flagged. It's a cosmic census, a map of the moving population, a way to spot hazards. In October 2017, the system flagged a dot. It was moving too fast, on a trajectory that was all wrong. That wide field gaze, that tireless repetition, caught the interstellar scout passing through. Without this survey, Oumuamua would have slipped by unseen. Just another speck in the dark. This changes discovery. For centuries, finds came from targeted looks or luck. Now they come from systematic, automated searches. Pan-STARRS represents a shift, from looking at the sky to reading it. Line by line for changes, it turned the sky into a data stream. And in that stream, it found our first known visitor. The telescope's design was suited for the task. Its wide field could cover enormous areas quickly. That increased the odds of spotting something rare and fast. It was in the right place, doing the right job at the right time. But Pan-STARRS is just the beginning. The next leap is already being built, on a mountaintop in Chile. The Vera Rubin Observatory. Its legacy survey of space and time will redefine what's possible. Its mirror is wider. Its camera is more powerful. Its scan will go deeper and faster. Where Pan-STARRS might see a faint speck like Oumuamua once, Rubin will see it dozens of times. Building a far more detailed picture of its path, its rotation, its nature. It will scan the entire visible sky every few nights with incredible sensitivity. This isn't an upgrade, it's a transformation. The promise is profound. Oumuamua will cease to be a solitary mystery. Within the first few years of Rubin's operation, astronomers expect to find dozens of interstellar objects passing through. We'll move from studying one enigmatic date, a point, to analyzing a population. We'll have statistics. We can ask new questions. How many are there? What's the average shape? The typical composition? Do some have cometary tails, while others are dark and inert like Oumuamua? This statistical sample is the key. It will unlock the truth. If most interstellar objects look like familiar comets, then Oumuamua was likely a rare fluke. But if a significant number share its strange properties, the lack of a coma, the extreme shape, the anomalous acceleration, then the paradigm must shift. We'll be forced to confront a possibility that the galaxy is filled with objects we don't yet understand. Objects that defy our natural categories. The tools are changing. Our vision is expanding. The next visitor won't be a shocking anomaly. It will be a data point in a growing catalog. And in that catalog, we may find the context. To understand what passed by us that autumn night, was it a herald of a common yet bizarre natural process? Or was it the first glimpse of a galaxy that builds things? The answer won't come from debating one object. It will come from discovering the next 10. Pan-STARRS gave us a trajectory, a line across the solar system. And for a moment, that line made you think, what if we followed it? This object was a once-in-a-lifetime thing, a piece of another star system sailing away. Could we build something fast enough to catch it, to see it up close? That question became a study, Project Lyra, from the Initiative for Interstellar Studies. They asked the hard question, with our technology, current or near future, could we launch a mission to rendezvous with Oumuamua? The answer shows our ambitions. And our limits. The first challenge is speed. Oumuamua was moving fast when it left, over 196,000 miles per hour relative to the Sun. To catch up, a spacecraft needs to go faster, much faster. It's like a police chase. The suspect is miles ahead, accelerating. Your patrol car has to match that speed, then exceed it, to close the distance. Project Lyra's calculations showed that, to reach Oumuamua in a few decades, the spacecraft would need velocities approaching a significant fraction of light speed. Speeds we've never achieved, not with a deep space payload. So how do you get that speed? The study looked at the edge of our imagination. One concept used the Sun itself. A spacecraft diving incredibly close, using that gravity as a slingshot. A tremendous boost. but it would need a heat shield beyond anything we've built. Another idea was nuclear propulsion. Controlled nuclear reactions for continuous thrust over years. High speed, but with immense political and engineering hurdles. Then there was the solar sail. The technology Oumuamua itself might have used. A giant, ultra-thin sail, kilometers across, propelled by nothing but sunlight. It could build up incredible speed over time, but it would need perfect deployment, and a launch vehicle to get it out of Earth's gravity well first. Then comes the timeline. Even with advanced propulsion, the mission lasts a human lifetime. A launch in the 2030s might not reach Oumuamua until the 2070s or beyond. The spacecraft would need to be autonomous, surviving interstellar space for decades before it got a close-up image. The navigation is a monumental task. You're aiming for a target the size of a football field, billions of miles away. Its exact path has tiny uncertainties that grow every day. You have to hit a moving speck in a cosmic ocean. Such a mission is beyond our immediate grasp, but its value is incalculable. It forces our civilization to think in timescales longer than a generation. To plan for discoveries our grandchildren might witness. Project Lyra reframes Oumuamua. It stops being a ghost we observed. It becomes a destination. A place we could one day visit. By drawing up the blueprints for a chase, we shift our mindset. From passive observers to active participants. We declare, with equations and reports, that the next time a visitor comes, we intend to do more than watch it fade. We intend to say hello. The chase is a dream for the future, but the reality is already here. We found one, then we found another one. The second one came just 2 years later, in August 2019. An amateur astronomer in Crimea, Gennady Borisov, he spotted it with his own telescope. A faint smudge moving against the stars. The trajectory looked suspicious right away. And the calculations confirmed it. This comet, 2I/Borisov, it was also from beyond our sun, but it was nothing like Oumuamua. Borisov was a textbook comet. As it got closer to the sun, it developed this beautiful, diffuse coma. A glowing halo of gas and dust. It grew a faint tail. You could see it outgassing. Its acceleration was exactly what you'd expect from that activity. Borisov was familiar, a cosmic traveler, but one that played by the rules we already knew. That second discovery changed everything. It meant Oumuamua wasn't a solitary freak event. Interstellar objects were real, and they came in different flavors. Some were dark and strange, others were bright and predictable. This wasn't a mystery anymore, it was a population. And if we found 2 in just 2 years, how many more are out there, unseen? Astronomers did the math. They took the volume of space Pan's stars was watching. They factored in how faint an object it could detect, and for how brief a window as something like Oumuamua sped through. The calculation is an estimate, but it's staggering. At any given moment, there could be thousands of interstellar objects within the orbit of Neptune. Thousands. Most are just too small, or too dark, or too far away for our current telescopes to pick up. They are the silent majority, passing through our cosmic neighborhood in the dark. Think of it like standing on a beach at night. You see one strange shell wash up. Then you see another. That tells you the ocean is full of them. The tide is constantly bringing new ones in and carrying others away. Our solar system is that beach. The galaxy's tides of stars and gravity are constantly sending visitors our way. Oumuamua and Borisov were just the 2 that happened to wash up while we were looking. This statistical view reframes the entire question. It moves us from wondering if something is out there, to asking what the distribution looks like. Are most interstellar objects like Borisov ordinary comets from other stars? Or is a significant fraction like Oumuamua odd and unexplained? The answer will define a new field. Interstellar object astronomy, no longer a theoretical footnote, but a branch of science with real data to collect. Every new visitor we find adds a point to the graph. It helps us understand the building blocks other star systems send into the void. It tells us about the composition of planetary systems light years away. And maybe it will tell us if any of those building blocks were shaped by something more than just gravity and chemistry. The cosmos is quiet. It's a question. The universe is so vast, so old, with billions of stars and planets. But it feels empty. That's the Fermi paradox. The numbers say civilizations should be common. But we don't see any grand constructions. We don't hear any clear signals. So where is everybody? Oumuamua offers an answer. A humbling one. Maybe they're not broadcasting. Maybe they're not even out there anymore. But their artifacts are. The galaxy could be filled with silent, drifting evidence. Civilizations that rose and explored and faded away. Their greatest monuments might not be cities, not signals, they're garbage. The spent stages of interstellar probes. Broken fragments of light sails torn over eons. A piece of technology, its purpose forgotten, tumbling dark and cold between the stars. Oumuamua fits that. It wasn't an active ship, it was driftwood. A derelict, and if that's true, it changes the search. For decades we've listened. Pointed radio telescopes at the stars, hoping for a hello, that's SETI. The search for intelligence. But if intelligence expresses itself in objects, not signals, then we need a different approach. We need to look for its archaeology. That idea has a name, SETA, the search for extraterrestrial artifacts. It means scanning the solar system, the space between the stars, looking for objects that don't fit the natural pattern. Treating every anomalous asteroid, every strange comet, as a potential artifact. A clue. Imagine walking through a vast, ancient forest. You might never see another living person. But you might find a rusted tool, a piece of pottery, a carved stone. Those silent objects tell a story. They prove someone else walked here before you. Oumuamua could be that rusted tool. A piece of galactic archaeology that floated into our yard. And that perspective dissolves the paradox. We are not alone. They were here. Their presence is written not in radio waves, but in the trajectories of strange, dark objects, passing silently through the night. The challenge now is to learn how to read that message in the stone. A single point of light, and the world noticed. Oumuamua. Its discovery moved out of the observatories, out of the journals. It became a global conversation. Front pages, social media feeds. The story had everything. Mystery, the scale of space, that possibility of contact. Headlines went for the provocative angle. Alien probe, interstellar spaceship. The artificial hypothesis from a Harvard astronomer became the hook. It was a compelling story, but it often overshadowed the more careful, nuanced debate happening inside science itself. This public engagement, it was a double-edged sword. On one hand, it was a victory for outreach. Millions of people who'd never open an astronomy journal, they were talking about non-gravitational acceleration. Light sails, interstellar origins, it made planetary science feel immediate. It felt thrilling. It inspired curiosity. For a moment, the whole planet looked up. They wondered about the same strange visitor. That shared wonder, it's priceless. It fuels support. It inspires the next generation of scientists. But the frenzy showed a tension. A deep tension in how science gets communicated. The careful language of probabilities, of competing hypotheses. It struggles against a headline's need for a definitive answer. An exciting answer. The public saw a clash, a bold claim versus skeptical pushback. And sometimes it framed that as a simple conflict. The visionary against the closed-minded establishment. But that misses the engine of science, that messy engine. The clash is the process. A scientist proposes an extraordinary idea so the community can test it. Stress it, try to tear it apart. The goal isn't to win an argument, it's to pressure test an explanation against all the evidence. The media spotlight, though, it often turns this vital scrutiny into a personal drama. We also saw scientists navigating this attention in real time. They had to communicate profound uncertainty. They had to explain that yes, the artificial hypothesis was a valid proposition to consider. But no, it was not a conclusion. They had to articulate why exotic natural explanations, even if they seemed far-fetched, were still more parsimonious to many researchers. More parsimonious than jumping to intelligence. This became a masterclass in modern science communication under duress. It required balancing transparency about the mystery with humility about the limits of the data. Some succeeded in conveying the beautiful complexity of the problem. Others saw their cautious nuances stripped away, leaving just a soundbite that fit a simpler narrative. So the public's engagement with Oumuamua, it's more than a sidebar. It's a core part of the story. It shows what happens when the frontier of knowledge collides with the public square. We saw the hunger for a cosmic connection, the challenge of translating uncertainty, and the enduring power of a good mystery, a mystery that makes us all look up. Look up from our daily lives and ponder that silent, dark ocean, the ocean of space through which these strange travelers endlessly drift. We've always seen the cosmos as silent, and that silence felt like proof we were alone. Just us, looking out at all that darkness, wondering if we were the only ones here to see it. But now there's this object, Oumuamua, and if it's what some think it is, that whole idea breaks. It's not just a scientific answer. It's something bigger, a kind of reverse Copernicus. Copernicus moved us from the center of things to just a planet orbiting a star. This would move us from being the only ones building technology to just one chapter. Maybe a late chapter. We wouldn't be the first, we'd be latecomers to a conversation that's been going on, maybe for millions of years in complete silence. And that changes the weight of everything. Our whole story of progress, from stone tools to telescopes, it becomes a local event, something that happened here. Remarkable, but maybe not unique. The galaxy might not be some untouched wilderness waiting for us. It could be an ancient landscape, already touched, already explored, not filled with civilizations we can talk to, but with what they left behind, their ruins, their relics just drifting. That makes the universe feel different. More crowded, but also older. Infinitely older. It turns us from lonely pioneers into archaeologists. We're not shouting into an empty canyon anymore. We're sifting through sediment, cosmic sediment, looking for fragments left by whoever was here before us, and that challenges what we think matters. A civilization's mark might not be a beacon of radio waves. It might be the quiet drift of something it discarded. Long after its star has changed, after its worlds are gone, these silent things might still be out there. They become the monuments, the only proof that a species once looked up, wondered, and built something to sail the stars. It reframes our own ambitions, too. Our probes, like Voyager, they're not just messages in a bottle for someone in the future. They might become archaeology themselves, silent, cold fragments of us, found by someone else long after we're gone. So Oumuamua's potential isn't about making space feel smaller. It's about making time feel deeper. It suggests technological epochs might rise and fall across the galaxy, separated by such vast time that contact is impossible. We're not neighbors in space, we're successors in time. Finding an artifact wouldn't be about meeting another. It would be about discovering we have ancestors. Ancestors in thought. It turns cosmic loneliness into a different connection, a connection across eons, a shared thread curiosity, engineering woven into the galaxy itself. The great silence isn't emptiness. It's the quiet of a museum after hours. Stories held in every dark corner, waiting for someone to turn on the lights. We have protocols for fires, for pandemics, for earthquakes, even for an asteroid impact. But for something from another star system arriving here, that plan isn't written. Oumuamua showed that. We saw it, we scrambled to study it in this ad hoc way, and then it was gone. The next one should be different. We need a playbook. An international plan for science and for policy, agreed on ahead of time. So we don't waste a moment when the next one comes. It starts with detection. The instant a survey telescope pans stars or the Vera Rubin Observatory spots an object on a hyperbolic path, an alert goes out. Globally, not just to astronomers but to every space agency, every relevant body. That starts Phase 1, immediate characterization. Every major telescope gets a priority override. James Webb, Hubble, the radio dishes, the observatories in Chile and Hawaii. They all coordinate. The goal is a full portrait in days, get the spectrum, map the light curve for shape, listen across radio bands. That means pre-negotiated agreements on telescope time and data sharing. Cutting through the usual delays. At the same time, orbital calculations become the top priority. We need the exact path with extreme precision. Is it on a collision course with Earth? The chance is tiny, but we have to know. That's where existing planetary defense frameworks would engage. NASA offers their international counterparts. They'd start modeling, but there's a new layer needed, assessing non-gravitational forces. If this object, like Oumuamua, shows an anomalous acceleration, the protocol escalates. It moves from a natural object to one of profound interest, possibly technological. That's where policy meets science. Current international space law through the UN is built for satellites and space stations. For the peaceful use of space, it doesn't address an interstellar artifact. If the data suggests something is not natural, if the properties point to an artificial construct who speaks for Earth. Who coordinates the response? Do we try to communicate, plan a rendezvous, or if it posed some hypothetical threat, consider deflection? These aren't questions for astronomers alone. They need diplomats, ethicists, legal scholars, representatives from across humanity. The discussion needs to have already started. A new framework, maybe a dedicated UN committee, for this specific, extraordinary scenario. The goal of this isn't fear. It's clarity, unity of purpose. So our response is driven by curiosity and caution, not confusion or panic. It turns a once-in-a-generation event into a managed, global scientific campaign. We'd learn so much more. We might even, if the chance is there, reach out. The next Oumuamua won't knock politely. It'll streak through our system. A fleeting chance for contact with another star. We should be ready to answer. The idea of a silent artifact. That it could be built. If it was, what was it for? A few possibilities. The functional probe. The classic idea. A craft on a mission. It enters a system, gathers data on planets, atmospheres, maybe signs of life. Then it moves on. If Oumuamua was that, it's likely dormant now. Its power source spent. A tiny radioactive pellet, finished. Its systems are silent. It performed its flyby of our sun, maybe of Earth. It stored its findings. Or transmitted them home long ago. Now it's just a husk, drifting, that fits the radio silence. A probe on a mission wouldn't broadcast. Not unless it found something specific. Its design would be light. Durable. A thin, reflective light sail for propulsion makes sense. The tumbling we saw could be a sign its stabilization failed. Centuries ago, in this story, Oumuamua was an active visitor. A robotic eye that looked at our world, recorded what it saw, and then sailed on into the dark. We didn't detect it working because its work was done before we even knew it was there. Then a second scenario, more somber. It's not a probe, it's debris. A piece of wreckage. Imagine a catastrophic accident in interstellar space. Two vessels or a vessel and space junk collide at a fraction of light speed. The energy would be unimaginable. It would shatter structures into a cloud. Some fragments might be large, like Oumuamua. They'd be twisted, irregular. Their original shape obliterated. This fragment, tumbling chaotically, could have that strange flattened profile from the forces that broke it. Its surface might be scorched. Reflective from vaporized metal. Its acceleration, that could be a remnant. A torn piece of a light sail, still catching photons. This scenario requires no intent to visit us. It's cosmic archaeology of a tragedy. A piece of someone else's history. A broken shard from a conflict or an accident that by pure chance drifted into our path. It's a silent testament that even advanced civilizations might not be immune to catastrophe. Then there's the most poetic idea, the monument, the message buoy. Not a tool for a task, but an object created for meaning. Imagine a civilization that wants to be remembered. They know their star will die, their world will change. So they build things meant to last. They forge plaques or structures designed to survive the eons, and they give them a gentle push, sending them out into the galaxy like bottles in a cosmic ocean. Oumuamua could be that. Its unusual shape and composition could be a deliberate signature, meant to stand out against natural rocks. Its reflectivity could be a beacon. Not for propulsion, but to catch the eye of anyone looking. Its tumbling motion might even encode information, in the pattern of its flashes, a slow, rhythmic message in its light curve. In this view, it wasn't exploring, it was declaring, "We were here." This turns the object from a piece of technology into a piece of culture, a sculpture, a tombstone, or a greeting. It was designed with the hope, however faint, that someday, somewhere, another intelligence would find it. And no, they are not alone in the universe's long history. Each of these stories fits the data, the dormant probe, the tragic debris, the deliberate monument. They all explain the silence, the shape, the acceleration. Choosing between them is impossible with what we know. But that's the point. It stretches our imagination beyond the narrow idea of a spaceship. It forces us to think about the full life cycle of a civilization. Its exploration, its accidents, its art, its desire to leave a mark. Oumuamua in its silence could be any one of these things or none of them, but by considering them all, we prepare our minds for a universe that is not just biologically diverse, but culturally and technologically infinite. The next strange visitor might tell a completely different story. The cosmos speaks to anyone who's listening. Sometimes the most important signals come from a backyard. The story of interstellar visitors really shows what amateur astronomers and citizen scientists can do. It's science with the doors open. A global effort where one person at a homemade observatory can shift how we understand things. Gennady Borisov showed that. In August 2019, from his personal observatory in Crimea, he saw a faint, fuzzy visitor. His sharp eye and quick report led to confirming 2I/Borisov, our second known interstellar comet. Without him watching, it might have passed unseen. Its familiar, gassy coma wouldn't have given us that second crucial data point. He wasn't with a big institution. He was an enthusiast, a watchman, and his discovery changed the conversation completely. It proved Oumuamua wasn't just a one-time fluke, but the contribution goes past that first sighting. Once a survey like Pan-STARRS flags a fast-moving object, the chase starts. Professional telescopes are usually oversubscribed, booked months ahead. That's where a worldwide network of amateurs becomes essential. They can pivot right away. When an alert goes out, backyard observatories everywhere can swing into action. They take follow-up measurements, pin down the object's position, track its brightness. This distributed network acts like a net with thousands of eyes. Catching details a single professional scope might miss because of weather or scheduling. They provide the continuous monitoring that turns one detection into a reliable trajectory. That's citizen science in its purest form. A distributed, responsive sensor array, powered by curiosity. The collaboration goes further into the digital space. Projects like Zooniverse create online platforms where anyone with an internet connection can help sort through mountains of telescope data. You might look at images from a sky survey, clicking to identify asteroids or classify galaxy shapes. It's not just busy work. The human brain is really good at pattern recognition, often spotting things algorithms might filter out. By opening up data analysis, these platforms use the collective attention of millions. They turn the public from a passive audience into active participants in the search. The next strange pixel, the next odd light curve, could be flagged not by a PhD in an ivory tower, but by a teacher or a student or a retiree on the other side of the world. This inclusive approach does more than just widen our observational net. It builds a global community of cosmic explorers. It creates a shared sense of ownership over a discovery. When the next interstellar object arrives, it won't just belong to astronomers. It will belong to the retired engineer who helped refine its orbit, to the high school student who classified its image online, to everyone who ever looked up and wondered. This democratization of the search might be one of the most beautiful outcomes of the whole mystery. It reminds us the universe is a common heritage. And the greatest discoveries often happen when we all decide to look together, each from our own vantage point, but united by the same awe. Every strange visitor has a chemical signature, a kind of fingerprint written in light. For Oumuamua and Borisov, that fingerprint was all we had. We couldn't touch them, couldn't bring a piece back. But we could try to read the story in the sunlight bouncing off them. That's spectroscopy. It's how you turn a faint point of light into a recipe. When sunlight reflects off something, certain materials absorb very specific colors. It leaves dark lines in the spectrum like a barcode. Ice, rock, metal. Each one leaves its own mark. And by reading that barcode, you can infer what the surface is made of. For Borisov, the comet, this worked. Its bright coma gave a clear signal. The spectra showed familiar lines, cyanogen gas, diatomic carbon. It looked like a comet from our own Oumuamua cloud, just visiting from another star. That was a profound finding. It suggested the basic ingredients for comets might be universal, that across light years, the processes in those cold, protoplanetary disks cook up similar kinds of dirty snowballs. But Oumuamua was different. Its spectral analysis was a struggle from the start. The object was already extremely faint and moving away fast. Telescopes had to chase it, gathering every precious photon. The data was noisy, ambiguous. Some studies said its color was reddish, like many primitive objects out there, tinted by cosmic radiation. Others saw a more neutral hue. The signal was so weak that a definitive identification of minerals or ices was impossible. We got a blurry barcode, not a clear read. This wasn't a failure of the science. It was a testament to the object's nature, dark, small, elusive. It guarded its secrets. That very difficulty, though, is a clue. Its surface, whatever it was made of, did not readily give up the spectral signatures of common ices. It remained an enigma, a locked box, passing silently in the night. Imagine if we could have held a piece, if a spacecraft had flown alongside it and extended a robotic arm to scrape a sample. What would that material have told us? We'd move from inference to fact. We could answer fundamental questions of cosmic chemistry. Are the ratios of key elements, carbon, silicon, iron, oxygen, the same in other star systems as they are here? Or do different stellar environments, different supernova histories, create different blends? The minerals themselves would be a history book. The crystalline structure of silicates, the isotopes trapped in the material. They could tell us the temperature and conditions of the disk where this object formed. Even the age of its parent star. This is comparative planetology on a galactic scale. By comparing the actual stuff of other systems to our stuff, we learn what's standard and what's rare. We learn if the recipe for building rocky planets is a universal constant, or if the galaxy has countless variations. A single grain from Oumuamua could tell us more about planet formation in its home system than a century of remote observation of distant exoplanets. This pursuit transforms these visitors. They become more than curiosities. They are physical samples, delivered to our doorstep by the natural dynamics of the galaxy. Each one is a free, albeit fast-moving, sample return mission from a star we may never study directly. They offer a tangible connection to the construction sites of alien worlds. The next one we find, especially if it's larger or brighter, might finally give us that clear spectral read. Or better yet, a future interstellar intercept mission might one day bring back a fragment. Until then, Oumuamua's stubborn silence on its composition remains one of its most tantalizing features. It reminds us that some of the universe's most important messages aren't written in radio waves. They are written in rock and ice, waiting for the day we are quick enough and clever enough to catch them and finally read their story. The push was so small. It was hard to believe. Just a whisper of force against something moving between stars. To get why that whisper mattered, you have to think about sunlight. It's not just light. It carries pressure. Every photon has momentum. When it hits something, it gives a tiny nudge. For us standing here, that pressure is nothing. You'd never feel it. But in space with no friction, on something with almost no mass, that gentle push can build. That's solar radiation pressure. It's the idea behind solar sails. We're testing that now. The question for Oumuamua was simple. Could sunlight alone have given it that push? To answer, you need numbers. We never knew its exact mass. That's the big unknown, but we can guess its size from how bright it was. Say it was about 100 meters across, shaped like a flat disk. The force from sunlight depends on two things: the area facing the sun and how reflective it is. A perfect mirror reflects almost all the light. It gets twice the push of something black that just absorbs it. If Oumuamua was highly reflective like polished metal, and if it was also incredibly thin and light, maybe only a fraction of a millimeter thick, then its mass could be astonishingly low. Think of a giant piece of aluminum foil, the size of a football field but thinner than a razor blade. In space, an object like that would have very little mass for its huge area. Now the math. Acceleration is force divided by mass. With a huge area and a tiny mass, that gives you a significant number. When researchers ran these calculations, using the estimated size and a reflectivity that fit the observations, they found something. The predicted acceleration from sunlight pressure matched the anomalous push in Oumuamua's path. The numbers lined up, not roughly but precisely. It wasn't a vague coincidence. It was a quantitative fit. The observed deviation from a purely gravitational path was exactly what you'd expect if Oumuamua was a thin, light, reflective object being pushed by sunlight. This mathematical alignment is the foundation. It takes the idea out of pure imagination and puts it in physics. It shows the object's strangest behavior. Its mysterious acceleration without any visible outgassing is perfectly explained by a known phenomenon if the object has the right properties. And those properties, extreme thinness, low mass, high reflectivity, aren't typical for a random rock or a fragile clump of dust, but they are the exact design specs for an efficient light sail. A civilization trying to send a probe across interstellar space would aim for maximal area with minimal mass. They'd make a smooth, reflective surface to catch every photon. The physics demands it. So when we see an object that behaves as if it fits those specs, the conclusion isn't a wild leap. It becomes a direct reading of the data. This dive into the mechanics doesn't prove the case, but it shows why the idea can't be easily dismissed. It shows the most extraordinary explanation for Oumuamua is also, in a real sense, the most straightforward one from a physics perspective. The universe gave us an equation with one variable missing, the mass, and the solution that makes everything balance points to an object unlike any natural stone we know. A scientific anomaly turns into a cultural icon. It goes beyond papers, it sparks stories. Oumuamua did that. Its mystery was unresolved, so it jumped from astrophysical journals. It went into art, into literature, into film. It became a canvas for our cosmic questions. Artists started with its form. Was it a cigar, a pancake, a disc? Renderings appeared. They showed a dark, slender shard against stars, sometimes with a faint glow hinting at propulsion. These images did something. They gave the unknown a shape. An abstract data point started to feel real. It felt physically present in our minds. It became a symbol, not just of an object, but of the encounter. The moment something from out there passes through here, writers adopted it quickly, a potent plot device. Science fiction novels used it for first contact, for ancient civilizations, for existential risk. In some stories, it's a dormant probe that wakes up. In others, it's a piece of a larger artifact, a clue in a galactic mystery. These fictions have a purpose. They let us play out the implications. We can feel the wonder and the trepidation on a human scale. They turn orbital mechanics and spectral analysis into narratives. Narratives of connection, of curiosity, sometimes of caution. This is how we process the idea, the philosophically weighty idea that we might not be alone. We tell each other stories about what that meeting might be like. Documentaries and TV embraced it too, with equal fervor. It became a central case study. Shows about searching for intelligence, about solar system oddities. They brought the debate into living rooms, the debate between natural and artificial explanations. They framed the scientific conflict as a detective story. They gave faces to the researchers. They personalized the pursuit of knowledge. This mainstream coverage cemented its place. Oumuamua's name and its mystery reached an audience far beyond academics. This cultural resonance isn't a sidebar. It's a vital part of the discovery's impact. When an object inspires paintings and novels and films, it stops belonging just to astronomers. It gets woven into our shared human story. Art and narrative help us digest the cosmic scale. They make the impersonal vastness of space feel relevant, intimately relevant. They explore the emotional consequences, the societal consequences that raw data cannot. By giving Oumuamua a life in our culture, we are grappling with what it means. Collectively, we are rehearsing for the future, for the day the next strange visitor arrives. When the question is no longer theoretical, by dreaming about it in our art, we are preparing our minds and our spirits for that possibility. The object itself is silent now, it's gone. But the conversation it started continues. The stories it spawned keep echoing. They shape how we envision our place. In a universe that grows more intriguing, more mysterious with every passing night. The point of light is gone. It's moving toward Pegasus now, away from our neighborhood. And maybe our best chance for a simple answer went with it. So we're left with the hardest question. Will we ever know what Oumuamua was? The reality is we might not. Not with this one. Our window to study it was brief and it closed. The data we have is all we'll ever get. That collection of numbers, light curves, orbital calculations, it's a permanent riddle now. A puzzle with pieces missing. That's exploration at the edge of our reach. Some visitors pass by once and leave a profound silence. But the quest doesn't end with this traveler. The most likely path to an answer isn't chasing a ghost we can't see. It's preparing for the next arrival. Oumuamua was a starting pistol. It alerted us to a whole new class of phenomena. The solution will probably come from studying what comes after. With better tools, sharper vigilance, we can be ready. Imagine catching an interstellar object early as it first enters the system. New telescopes like the Vera Rubin Observatory promise that. They could give us months, maybe years of observation instead of weeks. We could track it from approach, through its solar encounter and out into the depths. Take thousands of images, build a detailed movie of its rotation, any activity. Definitive evidence might be a high-resolution image, not a single pixel, but a shape resolved into contours. A picture from a powerful space telescope or a dedicated flyby mission could settle the debate about its form instantly. Is it a ragged, rocky shard, scarred by eons of travel? Or does it show geometric lines, panels, a manufactured smoothness? A close-up would tell us. Even more powerful would be a spectral analysis from up close. Sampling the surface chemistry without the blur of distance and speed, we could know its composition for certain. Stone, ice, or something entirely unfamiliar. The ultimate proof would be to touch it, to retrieve a sample. A mission to chase down an object like Oumuamua is a monumental challenge, but a future intercept of a slower or closer visitor isn't beyond imagination. A spacecraft, maybe propelled by a light sail, could rendezvous, extend a robotic arm, scrape a handful of material from its surface. Bringing even a few grams back to Earth would allow lab analysis atom by atom. The isotopic ratios, the crystalline structures, The potential presence of alloys or materials not found in nature, any of these could shout the object's origin. This acknowledges a truth of science. Some mysteries persist. They are not failures, they are engines. They drive inquiry forward for decades. Force us to build better instruments, think more creatively, collaborate more widely. The unknown isn't a wall, it's a horizon. Oumuamua expanded that horizon dramatically. It taught us to look at the sky with a new question. Not just what is out there, but who might have put it there. The quest for that truth is a marathon, not a sprint. A relay race across generations. We may never know about that first strange scout, but its legacy is the watch we now keep, the sharper eyes we're building, the curiosity it ignited. The next time something dark and silent drifts into view, we'll be ready to look much, much closer. Maybe we're framing this wrong. We keep trying to put Oumuamua in one of two boxes. Either it's a natural rock, or it's an artificial craft. But there could be a third option, something that doesn't fit any category we have. It might be the first example of something entirely new. An astrophysical object we've never seen before, so we don't even have the language for it. That's when science gets creative. When the data breaks the old categories, you have to invent new ones. So let's build one of those unified natural theories from scratch. Start with a catastrophic event in a distant star system. A planetesimal, a building block of a planet, suffers a huge collision. It gets shattered, but not into familiar rocky chunks. This body had a unique structure. A thick, dark crust of carbon-rich material like cosmic charcoal. And underneath, a core of almost pure nitrogen ice. Now imagine the collision strips away most of that dark crust, exposing the bright nitrogen heart. What's left is an irregular shard, tumbling away. Its shape is elongated or flattened from the violence. Its surface is now that reflective nitrogen ice. That solves the reflectivity puzzle. We're looking at a freshly exposed interior, not an old weathered surface. Then this nitrogen ice core begins its interstellar journey. For eons, it's just a dark, cold shard. Then it enters our solar system and swings near the sun. The heat triggers sublimation, but not of water ice. It sublimates nitrogen. Nitrogen gas jets invisibly from the surface. That provides the gentle, steady thrust, the non-gravitational acceleration. And because it's pure nitrogen gas, our telescopes, tuned for water vapor or carbon dioxide, detected nothing. No dusty coma, just an invisible engine. In this single story, you have an explanation. The strange shape from a violent birth, the high reflectivity from a novel ice, the acceleration from stealthy outgassing, all within a purely natural, if extraordinarily rare, framework. Another unified theory goes even further into the unknown. It looks not to planetary formation, but to stellar death. Around certain dying stars, conditions are bizarre. Temperatures and pressures we can barely replicate. In these extremes, some researchers speculate matter could clump in entirely new ways, not as solid spheres but as fractal aggregates. Imagine a snowflake but built on a cosmic scale. A delicate, branching structure of ice and dust, mostly empty space, held together by weak forces. This icy fractal could have a wildly irregular shape, explaining the extreme light curve. Its porous, complex surface could be highly reflective, bouncing light in strange ways, and its acceleration, that could come from the pressure of sunlight itself, pushing on that vast, feather-light structure. Like a dandelion seed catching a breeze, these ideas aren't proven. They're thought experiments stretching what might be possible in nature, but that's their power. They show science's response to a true anomaly. We don't just choose between existing options, we invent new ones. We ask, what natural processes, in the incredible diversity of the galaxy, could create an object with this set of properties? The answer might mean rewriting a chapter in the textbook on planetary science, or adding a whole new section on exotic interstellar debris. This third path is a reminder. Our catalog of the cosmos is still a first draft. For every common star and familiar comet, There could be 100 strange, singular things we haven't seen yet. Oumuamua may not be a message from another intelligence. It might be a message from nature itself, telling us our categories are too small, that the universe can make things far more wondrous and far stranger than we've dared to imagine. The greatest discovery might not be that we are not alone, but that we've only just begun to see the true variety of the cosmic workshop. Its identity is still uncertain. But its legacy is not. Oumuamua changed how we see the cosmos. It gave us proof. For centuries, interstellar objects were just a theory. After 2017, they were real. We know now our solar system isn't sealed off. It's a crossroads. Debris from other stars passes through here. That fact opened a new window. Astronomy has a way to sample the building blocks of other systems. A fleeting way, but a tangible one. We don't have to infer composition from starlight alone. We can study the actual material, if we're quick. This created a new field almost overnight. Interstellar object astronomy. Before Oumuamua, it was a textbook speculation. Now it's an active discipline, with conferences, with research, with telescope time. Scientists are building the frameworks for the next one. They're making classification systems for objects we haven't found. The Vera Rubin Observatory is designed with these visitors in mind. A whole branch of science exists because of one faint dot. It forced a revolution in theory, too. To explain it, astronomers went beyond standard models. They proposed exotic things, hydrogen icebergs, fractal dust clouds, ideas that push what we think can form in nature. That creative ferment is a direct legacy. It challenged scientists to rethink the end stages of planetary systems. What gets ejected when systems are born or die? The answers are reshaping how we see cosmic violence. How material is distributed, and it did something else. It brought the search for extraterrestrial artifacts in from the cold. For decades, the search for intelligence meant listening for signals. Oumuamua made a case for a different search, looking right here in our solar system for physical evidence. A civilization's signature might not be a broadcast. It might be a silent piece of technology drifting through. That shifted the paradigm, from communication to archaeology. It gave serious, quantitative grounding to an idea often seen as science fiction. Now, when we see an anomalous asteroid, the question isn't fringe. It's a legitimate hypothesis, to be tested. For the public, the legacy is re-enchantment. In an age where so much seems mapped, it was a reminder of how much we don't know, that first contact-level mysteries can still happen, that the universe can produce phenomena that stop experts. That forced them to question assumptions. It made planetary science feel immediate, suspenseful, human. Oumuamua did more than travel around our sun. It traveled through our consciousness. It left a mark on how we explore, how we theorize, how we dream about our place. The greatest gift of this scout might not be the answer it carried, but the better questions it taught us to ask. That faint dot of light is now part of our story. A single pixel on a screen, and it became a catalyst. It forced us to confront how strange the universe is. How wonderful it is. We followed its path from that first detection, through data that defied easy explanation, into the heart of a debate that stretches from the physics of light sails to the philosophy of our place in the cosmos. This journey with Oumuamua has been more than a scientific case study. It's been a mirror, reflecting our own curiosity, our caution, our capacity for imagination. We've weighed the possibilities. Was it an exotic hydrogen iceberg? A structure so fragile it challenges what we think can survive between stars, or a delicate fractal cloud? A cosmic dust bunny pushed by the pressure of sunlight, or perhaps, as some still argue, a relic, a silent piece of technology from a distant civilization. Its purpose lost to time, drifting as galactic archaeology. Each explanation asks us to believe in something extraordinary, and that's the point. Oumuamua's true identity remains a beautiful mystery. Not as a failure of science, but as a testament to its spirit. It marks the living edge of our knowledge, the frontier where data meets discovery, where certainty gives way to wonder. This mystery is an invitation to keep looking up, to build better tools, to think with both rigor and courage. Carl Sagan once said that somewhere, something incredible is waiting to be known. Oumuamua is a whisper of that promise. It didn't arrive with answers, it arrived with a question that has reshaped how we search the sky. Rekindled a sense of awe for the dark ocean between the stars. Let this strange scout be our inspiration, to search harder, to think bigger, to always embrace the profound and thrilling unknown. The next visitor is out there, moving silently in the dark, and because of Oumuamua, we will be watching.